For thousands of years, the night sky has been our greatest mystery. The canvas of a star stretched across the heavens, beautiful, distant, and silent. Yet, behind that silence, lies a story older than time itself. Our ancestors told myth to explain the constellations. Later, scientists began replacing legends with equations. Telescopes brought us closer, revealing galaxies beyond imagination. Still, the universe remained just out of reach, its first moments hidden in darkness. But we refused to stop searching. We built machines, launched observatories, pushed the limits of engineering and ambition, all for one reason: to understand the origin of everything. And that dream has now taken shape in golden mirrors, infrared vision, and a telescope that will let us see back to the dawn of the cosmos. This is the beginning of the James Webb Space Telescope. The Hubble Space Telescope changed everything. It gave us breathtaking views of the cosmos and answered questions we hadn't even thought to ask. But by the late 1990s, scientists realized Hubble was powerful, but not enough. It couldn't see far enough back into the earliest days of the universe. That's when the dream of a new telescope began. A telescope not just to look farther, but deeper. One that would see the light from the very first galaxies. Light so ancient, it has been stretched by time itself into the infrared spectrum, invisible to the human eye. In 2002, NASA officially announced the start of what would become the James Webb Space Telescope, named after the agency's former administrator who helped lead the Apollo program. But NASA wouldn't be alone. The European Space Agency and the Canadian Space Agency joined the mission, bringing their own instruments, innovations, and engineering. It was to be the most ambitious space observatory ever attempted, an international collaboration built not just to replace Hubble, but to go where Hubble never could. Back in time to witness the birth of stars, galaxies, and perhaps even life itself.
And we have engine start. And liftoff. Decollage, liftoff from a
On
tropical
December
rainforest to the end
25,
of time itself.
2021,
James Webb
the
begins a
James
voyage
Webb
back
Space
to the birth of
Telescope
the
launched
universe.
aboard an Ariane 5 rocket from French Guiana. Unlike Hubble, which orbits just a few hundred kilometers above Earth, Webb's destination was far more distant. Lagrange Point 2, located 1.5 million kilometers away. The journey took about 30 days, during which Webb performed hundreds of precise maneuvers. The most critical was deploying its 5-layer sun shield, the size of a tennis court, designed to block sunlight and cool instruments to minus 233 degrees Celsius. Next came the unfolding of Webb's iconic 18-segment gold-coated mirror, aligned with nanometer precision to capture faint infrared light from the early universe. At L2, the telescope entered a stable orbit, where the combined gravity of the Earth and Sun allows it to stay in line with our planet. From this vantage point, free from Earth's heat and light, Webb is perfectly positioned to begin its mission, looking deeper into the cosmos than ever before. The James Webb is more than just a camera in space. It is a masterpiece of engineering and avionics, designed to observe the universe in infrared light. It pushes the boundaries of what is technologically possible. At its heart is a segmented primary mirror, 6.5 meters in diameter, over 2.5 times larger than Hubble's, made of 18 hexagonal segments of beryllium and coated in a thin layer of gold. This mirror allows them to collect more light and see fainter, older galaxies than ever before. The beryllium ensures strength and thermal stability at cryogenic temperatures near minus 233 degrees Celsius. The telescope's sun shield, the size of a tennis court, is another marvel. Composed of 5 ultra-thin layers of haftan. It blocks light and heat from the sun, keeping the instruments cold enough to detect faint infrared signals. These layers reduce the sun's heat from 200,000 watts to just 0.02 watts on the cold side, a reduction by a factor of 10 million. To maintain alignment of its mirror, James Webb uses 126 actuators capable of nanometer precision adjustments. This means Webb can fine-tune its mirror segments within a precision less than 1/10,000th the width of a human hair. The onboard instruments, NIR cam, NIR spec, MIRI, and FGS NIR ISS together cover a wide range of the infrared spectrum, enabling observations from newly forming stars to ancient galaxies. These systems operate in perfect synchronization, controlled by advanced avionics and data management units built to survive the harsh environment of space. Together, these systems make James Webb the most sophisticated space observatory ever built, a triumph of modern avionics and international collaboration. One of the most astonishing feats of the James Webb is its ability to align its 18 separate mirror segments to act as a single giant mirror. Initially, each segment captures its own image, resulting in multiple scattered dots of the same star. Engineers then command tiny actuators behind each mirror to adjust their position at the nanometer scale. Over time, these individual reflections gradually converge into a single sharp image. This alignment process took several weeks and involved complex wavefront sensing algorithms. The final result is a perfectly synchronized optical surface with an accuracy of tens of nanometers. This precision is what allows James Webb to capture some of the sharpest and most detailed images of the universe ever taken. Before James Webb, Hubble was our greatest eye in space, revealing breathtaking images of galaxies, nebula, and exploring stars, but every eye has its limits. Hubble sees invisible and ultraviolet light, which means it can see through cosmic dust. Webb, however, observes the universe in infrared. This lets it look deeper, not just in space, but in time, to the very first galaxies. While Hubble's 2.4-meter mirror served us well, Webb's 6.5-meter golden mirror collects more light, allowing it to detect the finest signals from the early universe. Think of Hubble as a historian and Webb as an archaeologist, both uncovering the secrets of the cosmos, each from a different layer of the universe story. On July 12, 2022, the world paused as NASA released the first full-color images from the James Webb Space Telescope. What we saw was more than just beauty, it was history, unfolding in light. In its first image, Webb revealed SMACS 0723, a galaxy cluster so massive that it acted like a gravitational lens, magnifying galaxies over 13 billion years old. We weren't just looking in space, we were looking back in time. Soon after, Webb unveiled more wonders. The majestic Carina Nebula, dancing with clouds of gas and newborn stars. The Southern Ring Nebula, the dying breath of a star, and Stephan's Quintet, 5 galaxies locked in a cosmic ballet. But Webb's mission is just beginning. These early images hold only a glimpse of what's to come. Analysis of distant exoplanet atmospheres, studies of early black holes, and insights into how galaxies grow and evolve. In every photo it captures, Webb expands the edge of human knowledge, one image at a time. The James Webb Space Telescope is not only a scientific breakthrough, it's an engineering milestone. From precise attitude control to autonomous operation at L2, James Webb Space Telescope pushed the limits of modern avionics. Its sun-shield deployment system, cryogenic sensors, and high-gain communication antennas reflect advanced flight control and thermal management technologies. These innovations serve as a test bed for future deep space missions and next-generation satellites. The success of James Webb proves how avionics enables long duration, autonomous missions far beyond Earth, shaping the future of both space exploration and aerospace design. With the James Webb Space Telescope, a new era of space observation has begun. One where we no longer just observe, but analyze, predict, and even search for life beyond Earth. James Webb is a stepping stone. Its technology and discoveries lay the groundwork for even more ambitious projects. Space-based interferometers, lunar observatories, and possibly the first telescope designed to directly image Earth-like exoplanets. This isn't the end. It's a doorway. what we build next will depend on what James Webb reveals. And now, as we wrap up, let's take a look at some of the most breathtaking images captured by this revolutionary observatory. Windows into the earliest moments of our universe.